is more to do with an issue around polar orbits by satellites. And this is a point where a 2D projection of a globe starts to differ and starts to stretch and fall apart. So we've clipped that off just for simplicity. You can see that each color here is associated with a type of cloud across the bottom. Where there is no data, either there is no imagery, and this is where these elongated lines occur, or that we could not identify any clouds, which is unlikely, and most likely that there were no clouds there on that day. So you can see in the bottom right where there's Australia in the outback, where there's very traditionally very few clouds, or across the Middle East. That is simply because there was no moisture in the atmosphere. There were no clouds at that point. We then applied it across an entire month, and we were able to classify entire movements of weather systems and clouds across time. What does this look like in a way that the machine understands? Well, it looks like something like this. So this is the latent space. This is what the machine sees after it's learned to re-represent all of that satellite imagery. There are probably in the order of 100,000 data points on this single plot, and they're all grouping in a way that shows us how well bounded they are. You can see there's some uncertainty between classes 3 and 4, the lighter and the darker, the lighter green and the orange. But generally, these are in broad stripes, a complete difference to the structure we saw before. So we found a new way to represent, or rather we've taught a machine learning algorithm to look at data and not try and solve it straight away, but think about the data in a new way, and then use a second machine learning algorithm to look inside the latent space of the first machine learning algorithm and find patterns inside that then. Problem is, as lovely as this work is, how do we know it's right? How do we validate a model as complex as this one? Well, the easiest way is to go, we have labels. Great. So we know if things are right or wrong. So we could see how accurately we classify sort of the labels we know. And we did that. So we looked across the different classes. So this is all the different classes from CI for cirrus down to DC for deep convection. And they perform relatively accurately in a, that's fine. We have an 87.51% accuracy on average. That's not a bad rate at all. That's pretty strong for a machine learning algorithm, but it's not any good for us because less than 1% of our data is labeled. We know that the stuff that is labeled, we got right 87.51% on average, but that means nothing when the majority of our data has no way of checking it. So how do we make sure that this sort of semi-supervised problem is right? Well, can we test it physically? Can we look at the systems we're trying to describe? And this is the other reason why we picked a residual network in this way, an invertible one. The trick is the fact that it's invertible. We never change dimensions. We always preserve dimensions from left to right. What that means is, unlike almost any other machine learning algorithm, we can take the patterns we find in latent space or the understanding of features in the real world that the machine has, find patterns in them and push them back the wrong way through our machine learning algorithm. And we suddenly get our real world data back out on the other end again, but now classified and categorized, which we can then start to look at. So not only can we understand what the machine is seeing at the end and find patterns in them, but once we found those patterns, we can then go and see what those patterns look like in real life. To give you an example, this is how many times we saw certain clouds occur across an entire month. So cirrus, which are the very thin, wispy clouds you tend to see that often occur after a contrail from an airplane, or often layer thinly above other clouds, tend to be associated with land masses or follow flows around land masses, and they tend to be associated with transpiration as well. Those follow patterns. Stratocumulus occur where we expect them to. Stratus and deep convection even more so. At this time, we were working quite closely with the University of Oxford's Atmospheric, Oceanic and Planetary Physics Department, And they're able to validate with us that these are natural occurrence patterns in a way they weren't expecting. We're also to check another way, because we had liquid water paths as part of what CloudSat provided to us as a data set. We could then almost X-ray what we had. So we could look as almost like a cross-section. What you're seeing on the left, on the x-axis of each graph, is the height above sea level. And then across the right, that's the y-axis. Across the x-axis is optical depth, or in this case, almost how densely the moisture is at that point. And you can see compared to on the right, cirrus seems to be the most confusing. It shows a lot of activity very high up and more at the bottom. That's mostly to do with the issue that cirrus overlaps other cloud types. It's what often is described as a mixed cloud type. But stratocumulus, that's very common where I am in England, where it covers the sky and it's flat and grey and nothing happens and it doesn't rain, it's just flat, is exactly the structure we expect, where everything's very densely condensed. Cumulus, zones and rising, shows that optical pattern as well. We've gone through every type we've looked and they are all following physical parameters. Even better, if we average these across time and compare them to theoretical, not theoretical, but measured models of the average of every single cloud type, which is in the darker blue line, and then the three-dimensional data we have on what we've identified as those cloud types in light blue, we are finding very, very close matches to what we see in nature. And although we don't have a way of putting numerical value to the accuracy of this model, the fact we are accurately capturing these kind of physical parameters when we've never trained our models to look for them is a huge way of validating this kind of work. As an output of our research, we've released the Cumulo dataset we use to train this data. There are some weaknesses. So sometimes a single pixel can have multiple classifications. So a single part of a cloud, often this is cirrus cloud, where a light wispy cloud is over a thicker cloud underneath it. In nature, certain cloud types happen more than others, and this is true in our dataset. And finally, because only 1 in 1,350 pixels are supervised, it's what's considered a very weakly labeled data set. However, it's open and free for public use, and it's a great way for cloud physicists and machine learning experts to apply to a brand new data set they haven't had access to before. Now, there's another set to this, understanding how these clouds, once we classify them, are useful for understanding our changing climate. And this illustrates it quite well. These 4 images are 4 images of cloud structures. And although, I might suggest that one of these is what's called stratocumulus, your classic storm cloud, they all are. If you were to look at these clouds from a boat or from land and look up, they would all be the same pattern, and a cloud expert looking from the ground would classify them exactly the same. Yet it's clear they have differences. It's clear the textures are different, it's clear the systems that form them are different, and it's clear that these must have different impacts on the climate, whether it's a storm system in the bottom left, whether there's clear, sort of on the top left, there's actually clear trails caused by, of all things, shipping containers and cargo ships. They burn bunker fuel that sends so much pollutant up into the atmosphere that it causes trails of clouds that can be tens of kilometers wide. Other things we don't quite understand in the top right is this weird pattern where suddenly there's a pocket of open air, what's called pockets of open cells. Now the moisture in them is very similar to any other cloud, but the cloud isn't forming there, it's pushing away. We still don't know why that happens. And we're worried that if that continues for longer, we'll still have the same moisture in the atmosphere, but less of a way to reflect sunlight, which will only accelerate climate change. And finally, at the bottom, a more typical weather front across an ocean. Yet these are all different textures for the same cloud type. And this comes back to this idea that we're starting to see some very significant changes in how clouds are interacting with the climate. They've always had these behaviors, but they're changing more now than ever, and we don't know how to describe them or even classify them in the first place. You have to do it from top down. You can't see these structures from the ground up. Well, again, we look at this ability to do representational learning. So again, we take the data that we've found a way to re-represent using an invertible residual network. And instead of trying to find classifications and groups across every single type, what happens if we just, I don't know, look at one type, maybe the light blue, and we remove every other data point from there, and then we cluster again just on that? Will we find additional patterns in there? Normally, if you run this on any output from a machine learning model, it is meaningless. You will get results out, but they do not reflect what's happening in real life. Yet because the distribution of data on the right is tightly coupled with the physical, real, measured data on the left, we can do this. So to test this idea as to whether this was possible with the data we collected, we took a slice of the ocean. We chose the Southern Ocean because mostly there are no land masses in the way. If you go too far north, you hit ice. Too far south, you hit ice as well. Yet there is a small band of about, well, I say small, it's about 10 degrees in latitude wide, with very few land masses in the way to interfere with cloud formation patterns. We took 2 case studies out of this. This might seem small, but you know, these are hundreds, if not thousands of kilometers wide and tall each, and show entire weather systems in their own right. And we ran our cloud classification machine learning on it. We found they were 2 very similar types. We wanted to focus in particular on the cumulonimbus, or the green type. Now we can see in the bounding boxes here the purple, pink, and green. The both green boxes here are of a particular weather type, a particular cloud type texturally. They're all the same type from the ground up in our classic classifications. Yet you can see these dispersal patterns behind them, which are clearly very different in the way that we'd see them from space. Yet they're still the same type. But what happens if we isolate everything else and we just find new clustering patterns on this data? Well, we get something quite interesting. We start to pick up changes in texture. What's very interesting here is the fact that we never taught our machine learning algorithms to look for texture. Texture in the sense that we looked for 3 pixels by 3 pixels, yes, but larger changes, it's not a convolutional network. It doesn't have a way to understand if this is in one part of the image, then on the other part of the image, if there's this, this means this. It doesn't work that way. Which means that not only is it picking up textual changes, but there's clear physical differences inside these clouds, which means actually these aren't just textual changes for the sake of them. This is a changing type of clouds in a way that's responding to our climate, which is also an industry first. So we're very excited about it, or at least an industry first for this scale with the machine learning. The takeaway points I want to say here are, yes, for cloud classification, but actually there's more general lessons as well. Often satellite imagery for any kind of machine learning or even analytics, it's very rarely restrained by the quality of the data you collect or the quantity. There's decades and decades of satellite imagery of every sensor possible, every resolution in time and in space possible within reason. Often it's because you're not sure what you're looking at, and it's a huge effort to hand label this kind of imagery. So it's labeling that defines the quality of any analytics you do, whether in the public sector, the private sector, for research, for fun, for business. Secondly, we can see how we've been quite blind to how sort of clouds are changing because we've sort of put them in these very old classifications, you know, nimbus, stratus, cumulonimbus. These are no good. They might allow us to look up at the sky and go, oh yes, that's a stratus, but it doesn't capture the changes in the climate in a good way. We must let the data we hold dictate the classes that we use, not the other way around. This holds as true if you're doing market research for a, you know, for retail. Don't go, well, I expect to see, you know, maybe men who are 40 must buy this way and men who are 20 must buy this way, and these are 2 types. Let your data talk first and then work out which clusters belong to who. And the last one is latent space techniques. Things like residual networks and invertible residual networks offer brand new approaches. These have only been around for 2 years properly, and they will allow us to completely change how we measure, interact, and understand this kind of complex data, which was considered previously impossible. I didn't do this alone. I worked with a research team of 3 other researchers. Valentina Zantedeschi, who is now at General Electric, but had won the best AI thesis in France in 2019. Very talented climate physicist called Fabrizio Falasca, a cloud physicist called Alison Douglas, and myself. And it's much more than that. We weren't able to do this without the funding and support technically and in sponsorship, just through the graphics cards we needed to run this kind of work, through to the storage space, through to the advice, through to the research access of all of these partners. The entire thing was run by a body called the Frontier Development Lab, and worked very, very closely with ESA with our projects, and it's part of 11 different projects, half of which have also worked directly with NASA.